stoichiometric, which kind of means that the flame length is where the stoichiometric contour hits the center line. Okay? And because now, interestingly, because we can bring the flame length back to this non-reactive scalar, essentially we just need a solution for this non-reactive scalar and anything else that's related to this. So these are the equations: continuity, momentum equation, mixture fraction. And here again we introduce a similarity transformation. A similarity coordinate here, eta, is again this mass-weighted coordinate. That's very typical in combustion problems. Whenever you want to get a similarity solution, the density is kind of in the way, and you want to take the density out, so you introduce mass-weighted. This kind of a mass-weighted coordinate, the density times RdR. And then psi here, that is a coordinate here in x direction. So this is the main flow direction, and this here is a coordinate in the radial direction. But again, a mass-weighted. And then second, trick that you always do when you look for similarity solutions, introduce a stream function. The introduction of the stream function has a consequence usually that the continuity equation is inherently satisfied, and so you don't need to. You have decreased the number of equations that you need to worry about by one. So then introduce, these are the transformation rules. If you introduce then this transformation and make a few more assumptions here, for example, about this so-called Chapman-Rubizin parameter, which essentially gives you the Chapman-Rubizin parameter is here mu divided by mu infinity, essentially. So that gives you the change with temperature of the transport coefficients that you see here. This parameter appears here very often. It is assumed to be constant also. Okay, so this is the stream function here. This is the velocity. So let's put that all in, and you can solve the system. You put this all in, and you get an equation here like this. You can solve this, and you get a solution here for the stream function. And this omega here, that was the non-dimensional mixture fraction. And the only thing that's important here to realize is that there's this parameter here, gamma, which is not determined yet, is a kind of an integration parameter. And here this, to back out the mixture fraction here from this omega, also there's another parameter that we need to determine, and these just come from the momentum conservation. From momentum conservation, you can determine this spreading parameter here. And then you see here, you have an expression here for the velocity, and then here the next page probably. So this here is the momentum conservation integral that is used to determine this gamma parameter. And then a similar mixture fraction conservation integral is used to determine here this mixture fraction on the center line as this. Anyways, you get a result here for the mixture fraction in terms of here the diameter of the nozzle and things like that, and then one can set this equal to stoichiometric, and then solve this for psi. Here, psi is the spatial coordinate, and then that gives you the non-dimensional flame length. And this non-dimensional flame length, that's the result that's given here. And again, we're skipping all the little details, and if you are interested in these, look back at these. The main point I want to point out here, of course, now, the lift of length is related here to Z stoichiometric. The small, not lift of length, the flame height. The smaller Z stoichiometric is, of course, the longer the flame height, which explains some trends you observe when you, for example, dilute the fuel, because if you dilute the fuel, then the stoichiometric mixture fraction moves around in this space, or if you have EGR and the stoichiometric mixture fraction moves around in this space, and that then gives you changes here. Second thing that's interesting here depends on the density change and the density ratio between fuel and air, and then on this Chapman-Rubinstein parameter. But even more important, and that's the main point here, you see it depends on U naught, which is the main flow velocity, times the diameter divided by the kinematic viscosity, and that is what?
Reynolds number.
That is the Reynolds number. So it depends on the Reynolds number, and what this says is the larger the Reynolds number, the longer the flame length. Okay? Those of you who know something about turbulence should think now, oh, that doesn't make sense to me, at least when I think about turbulence, because in turbulence what we often say is as long as the Reynolds number is high enough, larger than 0, or large enough that flow becomes turbulent, then the flow becomes independent of the Reynolds number. Okay? So you see here for this laminar, but this was a laminar case, it wasn't a turbulence case, and for the laminar case, this depends on the Reynolds number, which means that if I increase my flow speed, then the flame height, the flame length should change. And I observe this here in my cigarette lighter. This is high flow rate, higher flow rate, small flow rate. Okay? We demonstrated at the resulting slides. Okay? So you see that actually when you look at the real flame. Okay, good. So that's there's this thing about single droplet combustion. That is very interesting for those of you who have an interest in multi-phase combustion. This is might be of interest. Did you have a question? No. Any questions about this before we move on? No. So. So we talked about this, flamelet equations and so on, and I showed you that using these flamelet equations we can explain a few things, that are interesting. Actually, they tell us a lot about, these little details that I mentioned earlier. Now, we will use this model later also as a combustion model for turbulent combustion, and this is really the reason why we have derived this. Okay, so now we switch gears completely, and we want to talk about turbulent combustion. And in order to talk about turbulent combustion, I thought I should give you an introduction into turbulence. Now, for those of you who don't know turbulence, it might not be enough to really appreciate the details of turbulent flows. I teach a course which is a whole semester on turbulence, and even that is quite short. And for those of you who know turbulence already, this might be not very interesting. So I don't know if I'm doing anyone a favor talking about this, but I would still do it. Hopefully, even though some of you know all this stuff already, you can relax a little bit. So this is a kind of a long chapter here, and we go through different things. I'll talk about statistical description of turbulence first. I will talk about some of the turbulence theory that might be helpful, introduce the so-called K-epsilon model. Everyone has heard about this, without giving too many reasons why this model is used. Then we'll talk about a few combustion models, which we will not cover then in any more detail, just very briefly, so that you have heard, know what the term means, really. And then, if we have the time, we'll talk a little bit about LES, or what's special in Largeeddy Simulation. Okay, so most of the engineering applications that we are looking at are turbulent. And I mentioned this before. The reason is that, roughly speaking, I said if you want the same heat release to happen in a laminar flow, it needs to be about the device needs to be at least 100 times larger than for the turbulent flow. And so because usually we want to have small devices, we want to make use of turbulent mixing, which then gives us heat release on a smaller scale. It's also hard sometimes to keep flows laminar if you want to have things happening on a large scale. So turbulence is hard to describe. Turbulence has some deterministic parts to it, but it's random. And so what this means then is that one has to resort to models or statistical models. And turbulence models have been proposed in the past in the literature, models that describe turbulence. And what the turbulence models really do is they model the random part of the turbulence, and they give us back the deterministic part. Okay, so we'll talk about mean values and expectations and things like that. Okay, in order to derive these turbulence models, one has to introduce closure hypotheses, and these are very often and fully empirical or semi-empirical. And when it comes to turbulent combustion, you're constructing these closure hypotheses will become even more complicated. Okay, so we do have models for turbulent flows. For example, there's the mixing length model, and there's the K epsilon model, there's the K omega model, and there are other models that you might have heard of. And many of these are based on the so-called Reynolds averaged approach. And the Reynolds averaged approach basically does let's say a time average of the flow and just gives us the time averages. Or for flows that are not statistically stationary, it does an ensemble average. It gives us the expectation that you would get after running the same experiment, let's say running the same experiment 5,000 times, and then taking the average over these 5,000 different samples. So that's what turbulence models do, and these turbulence models, they have been successful in predicting certain things, certain aspects. Turns out that these Reynolds averaged models, typically they have to be tuned, or they're good for a certain case and not so good for other cases. But by now people know what model is good for what case, and so you get some. You have a tool that gives you some results, and you kind of know what to expect from it. An example for this is if you have separated flows like a jet, and the K epsilon model turns out to be all right. If you have a round jet, though, the K epsilon model fails, and there are different coefficients that you use. Okay. And if you have wall-bounded flows, turns out the K epsilon model is not so good. The K omega model is much better. Okay. And so on. So as long as you know what to expect, fine. Now, for combustion, the situation is a little different. Because in combustion, one of the real problems is that, we talked about this earlier, are the very, very strong nonlinearities. These very strong nonlinearities, they have the consequence that very rare events can have a leading order on the dynamics of a system. Okay? I'll give you an example. Again, take this lighter, and let's say I'm outside. So this thing is burning. Turn it up a little bit. Thing is burning, and let's say I'm outside. It's a little windy. Okay? And I can hold this thing here for half an hour, and nothing happens. And all of a sudden, there's a gust here. It comes from the side, and it isn't burning. Okay? This was a leading order change in the dynamics of the system. Okay? Now the gust is gone, but my thing is still not burning anymore. And that same thing is true for you know, I'm talking about the cigarette lighter. That is true for, we see these effects, these very strongly nonlinear effects. We see these in many applications, and especially when it comes to pollutant formation. For example, these very strong nonlinearities, even if it doesn't lead to blowout, you know, can cause huge changes in the solution. Okay, so rare events is something. If you just solve equations that give you the mean values, the expectation, you have no clue what rare events can happen and how often they happen. Okay, so that is why these Reynolds average approaches for combustion, you know, they sometimes work, but they're not great. Okay, there's some things like soot formation or so where we know we cannot predict this with the Reynolds average approaches. Now, in the past years, the Largeeddy simulation technique, which some of you might have heard of, you know, has become more prominent in the combustion world. Turns out, with Largeeddy simulation, where you don't just solve for expectations, where you actually solve a part of the random motions also of the turbulent field, not all of it, but a part of it, let's say the dynamically important part of it. And if you do that, it turns out you get much better results. Okay? That technique is more expensive, it's a little more complicated. Numerics, you know, are very complicated and all of that. But if you do it right, you get really good results. Okay? Results are much more predictive. They don't depend on if you have a round jet or you have a, you know, whatever. So that's very good. That's one thing one should keep in mind about these models. Okay. Now, what is the problem? Or what? I mean, this is one of the problems. What is another problem in modeling combustion? Turns out in turbulence, the dynamically most important part of the turbulence is, you know, the large-scale motions. Okay, and the large-scale motions, let's say, they are relatively easy to predict. In LES, that's exactly what we do. We solve for the large-scale motions. But the small-scale motions, they are, you know, they're so small they cannot be resolved. But the combustion all depends on the small-scale mixing. Okay, and so that's one of the problems that you have in modeling turbulent combustion is that if you just want to model the turbulence, all the turbulence models, they would just tell you something about the large-scale motion of the flow. But combustion depends on the small-scale motion. The small-scale motion, that's where the molecular mixing takes place. And the combustion model, the turbulence models, they don't tell you anything about that. Okay? So that's one part of the problem. Okay, so there is the assumption of an energy cascade. If you think about a turbulent flow, let me see if we had a picture here somewhere. Maybe that's too far. Yeah. We have a picture here somewhere. So you have let's say you have a jet like this, and that jet, you don't need to go there. I just want to show you this picture, and I'll go back to where I was. You have a jet, you know, it goes into, you know, quiescent air or whatever. Then you have shear. The shear layer might become unstable if the momentum is high enough that viscosity doesn't dampen instabilities. That shear layer might become unstable, and it breaks up, and it might form these vortices. Now, when we want to conceptualize turbulence, then we often think in terms of eddies. Okay, and the notion of an eddy is not exactly right, but it helps a lot in trying to think about turbulence. Okay, so when I say we have a turbulent eddy and that breaks up into two smaller eddies, don't think you have a turbulent eddy that breaks up into two smaller eddies. But you know, it just helps us visualize this a little better. Okay, so you form these large eddies that now inherently they must be of kind of the size of the geometry. Okay, if I have a super huge nozzle, I form very large eddies. If I have a very small nozzle, I form very small eddies. Okay, So the large eddies that are produced by the shear, they are of the size of the geometry, and then you have different eddies and they interact with each other. And by doing that, they break up into smaller eddies. Okay? And these smaller eddies then, they are a part of the larger eddies. Okay? You have a big eddy that goes like this, and in the big eddy you have smaller eddies that do something else. And then these smaller eddies, they interact with each other, they form yet smaller eddies, and so on. By going from large to small, what you do is essentially you increase the local gradients. Okay? If I have a large eddy like this, it has from left to right, it has a certain change, and that's a large change, let's say, of the temperature or of the velocity. And because it's large, the gradient is relatively small across this. But now, if I break this up into smaller and smaller pieces, then the length scales become smaller, and it turns out the gradients become larger and larger. And why is that important? Because when the gradients become smaller and smaller and smaller, you all of a sudden viscous transport or molecular diffusion gets faster and faster, and all of a sudden it gets so strong that it dissipates these eddies. Okay, the eddies just go away. Okay, so that is kind of the notion of what's called the energy cascade in turbulence. Okay, that's one of the the foundations of turbulence theory is this energy cascade. Energy cascade again means turbulence produced at the large scales because it comes from the mean shear of the configuration, which is something that appears on the scale of geometric scale of the problem. And these large eddies, by nonlinear interaction with each other, so-called vortex stretching, they go to smaller and smaller eddies. And while the eddies become smaller and smaller, this looks like the eddies become larger and larger actually, but while you go downstream, actually they do become larger while you go downstream. But locally, they get smaller and smaller, and by doing that you increase the gradients. And for these large eddies and for the intermediate eddies, the viscosity or the diffusivity is not important at all because the Reynolds number is large. Okay, these effective nonlinear processes, they are much stronger than viscosity. Okay, you go to these smaller eddies, then all of a sudden viscosity becomes important, and you dissipate these eddies away, and so there's a below a certain scale there are no more eddies. Okay, so let me go back again, see what I wanted to say here. This is probably what was mentioned there. So in order to describe this, we use statistical methods. And these statistical methods, they are based on the notion of distribution functions and random variables and probability density functions. And probably all of you have heard these terms. I just want to introduce the notation here. So if you have a variable here, like the velocity component u, there is a distribution function where you can say, so let's say you have a turbulent field and you measure the velocity at one point. You do many measurements of velocity at one point, and you get different values for the velocity at that point. And now there's a distribution, or a so-called cumulative distribution function, f of u, which gives you the probability that u is smaller than a given value. Okay, so you fix a value capital U. You say is 5 meters per second, and then you can evaluate the probability for which u is smaller than these 5 meters per second. You can actually, so let's say that's 30%, and then you can vary this capital U. You can make it infinity, and the probability of finding velocity lower than infinity is 1. And you can make it minus infinity, and probability of finding a velocity smaller than minus infinity is 0. You cannot find a velocity smaller than minus infinity. Okay, and so on. So this is a function of this capital U, which is the value you specify. This is the so-called sample space variable. Okay, and so so for each value of u, you get a probability, to find the velocity smaller than u. Okay. So that's the cumulative, so-called cumulative distribution function for the sample space variable. Minus infinity is 0 always. For plus infinity is 1 always. Okay? And so in between it varies from 0 to 1. So we distinguish between the sample space variable, capital U, and the random variable, which is the one we measured. The random variable is the one we measure, the sample space is the one we compare it with. Okay? So now from this cumulative distribution function, we can derive the PDF. The PDF then is just df du. So the derivative with respect to the sample space variable. And this is how this looks like. So the cumulative distribution function looks like this. This here is f, and this is u. And so what you see here is, there's a velocity is so small that I can't find the measured velocity smaller than that. And then here the probability goes up, and then at some point I cannot find, I find all my measurements are smaller than this value of the velocity. Okay? Take the derivative of this, and it looks like this. Okay? So that's the PDF. That would be now something like a Gaussian PDF that I'm drawing there. And it would give you the probability density of finding a velocity in this region. Okay. There's a normalization condition here of the PDF. So if I integrate over this thing, the integral has to be 1, otherwise it's not a PDF. Good. These are details. The PDF is a function of the sample space variable, and it's a function of space and time. Because, if I do this measurement in different places in space, I get a different PDF. And so you see here that we want to distinguish between these two. Typically, we first put the sample space variable, and then semicolon, and then the independent space and time coordinates. Now, here in the following, I'm not sure if we use this very often, but we don't. So you need to distinguish between the sample space and the random variable. Again, here uppercase is sample space, lowercase is not here, would be random variable, but very often we don't distinguish here. So we just use the same symbol. When we say we have a PDF of temperature, we call it P of T. It's not right. Okay, you should call it P of some other symbol because it's not the random variable, and so on. So we don't distinguish, but you always need to know which one is we mean when we use the symbol. Now, if you have the PDF, then from the PDF you can get the moments of the PDF. But just by integrating a function like this, you see here we call the moment of the PDF here. Then we denote this here with a bar, or this integration we denote it with a bar. And then you see that the first moment is just the mean. Okay, that's the expectation, or the average, or whatever you want to call it. And you see here we denote the average here with this overline. And so if you have a function of u, integrate this with the PDF, then also get the mean of that function. Okay? So these are just, you guys know this. This was just reviewing, PDF and cumulative distribution function. Now, and introducing some notation. Now, in order to derive the equations that describe the mean, we said earlier turbulence has kind of it has an expectation. If I have a turbulent jet and I do a measurement here, always at the same point, I can then take the average of all my individual measurements, and I get a mean value on expectation. And really what we're interested in engineering is this expectation. We're interested in kind of the mean values. Okay? So if we want to derive equations that describe this mean value, we typically introduce what's called the Reynolds decomposition. So we take the the local instantaneous velocity, and we split it up into two parts. The expectation plus, well, actually this is just the difference between the mean or the expectation and the real local value. We call this the fluctuation. Okay, so, and this is how this looks like. Let's say I measure the velocity here at one point in space in a turbulent jet. This is the velocity, this is a function of time. So then I get something that looks like this. Okay? And you see this is kind of the expectation here. And then you see the expectation is independent here of time or whatever. Well, if it is statistically stationary. And then at each point here, at each time, I have a fluctuation. And is the departure from the mean. We call this u prime. Okay. So this is the random part. This is the deterministic part. Now, you can introduce this now, this decomposition, into the momentum equation, and you can derive the mean equations. Now, when we talk about combustion, there is a problem, and that problem is that you need to introduce this decomposition for the velocity, but also for the density. Okay, and then you see you get a lot of products here of u prime, rho prime, and so on. And so you get a lot of these nonlinear terms, which one tries to avoid. And so to avoid these, we often use, or usually we use, what's called the Favre average. So this would be, or the Favre decomposition. So rather than splitting this up into this u bar and u prime, we split it up into a u tilde and a u prime prime. Here, the assumption is that the average of u prime is 0. You see that? Why that's the case? If you have u is equal to u bar plus u prime, and I didn't tell you why that is. We didn't really, I didn't tell you why that is, but if you take so if you have the mean, you take the mean of the mean, it gives you back the mean, okay? It doesn't change. So if I take the mean on the left and on the right side, then you see I get this. This here is again the mean. You see these two cancel out, and the result is that u prime mean is equal to 0. Okay? So that's the assumption in the Reynolds decomposition, that the mean of the fluctuation is 0. Now, here we make a different assumption. We assume that rho times u prime prime bar is 0. And what this means then is that rho u mean is equal to introducing here this decomposition for u. You see you get a term here that is rho bar u mean, and you get a term here that is, well, that by definition is 0. So this is equal to this. So by introducing this so-called Favre decomposition, you reduce the number of terms that you need to worry about after doing this. And this is shown here. So take this term. This is, of course, a term that appears in the momentum equation. That's in the convection term of the momentum equation, or the nonlinear term. If I introduce this Reynolds decomposition in here, then you see I get, so I get a u mean plus u prime, and a v mean plus v prime. And so I get this term with the means here, and then I get, I get a rho mean plus rho prime, and then you see you get all these terms here that are kind of correlations of different fluctuating quantities. But if I do the same thing here for the Favre averaging, then you see you end up just with 2 terms. Okay, so there's 1, 2, 3, 4, 5 terms. Favre averaging only 2 terms. Okay, so that's why we use Favre averaging anytime the density is also a random fluctuating quantity, which it is in a turbulent reactive flow. Okay, so I'll skip this here. This just shows you how to get from the Favre, from the PDF to a Favre PDF. You can look at that if you want. Now, next step here is to then introduce this into the Navier-Stokes equations to derive equations for the mean, and then also to introduce turbulence models to close these equations. So now this is a classical procedure. It's based on one-point averages. One-point average is what we just introduced. If you introduce this, then it's called in the momentum equation and derive the momentum equation for the mean. That's the so-called Reynolds average Navier-Stokes equation, or it's called RANS. Which then, if for non-constancy, we do this using these Favre averages. So these are the equations here. This is the continuity equation and the momentum equation. And now you can introduce these Favre decomposition and then average the whole equation one more time, and then this is what you get. And interesting is that anytime you have a term that is linear, then you will see that the term, the average term, is or the average equation, or let's say, if you have a term that is linear, then the average equation will look just like the instantaneous equation. Okay? So for example, here, continuity equation looks like this, okay? And the average continuity equation looks like this. Okay? It's just the same thing, just with the bars and tildes on top. Okay? However, if you have a nonlinear term, then that nonlinear term, and that was shown here, this is a nonlinear term, or here nonlinear term, that will always give you two terms. Okay? Because now, for linear terms, you always get a fluctuation mean, and that was 0 by definition. And for the nonlinear terms, you get a fluctuation times a fluctuation mean. And as long as these two quantities are correlated, it's not 0. Okay? And so, of course, the velocities are correlated with each other, which is why you get a term here like this. Okay, so introducing this then, you see here, this is a linear term, or linear in velocity. This doesn't change, just the same time-dependent term. This is a nonlinear term, so you get this term here and this term out of the advection term. Pressure, and this is the viscous stress, and this is gravity, and all of these are linear, and so they just look like in the undisturbed equation. So you see that this is very similar to the original equation, except for this one term. Is this term important or not? Is this term important or not? Yes, it is important, because that is what makes the difference between the turbulent flow and the laminar flow. When I said this jet engine, with a laminar flame, has to be 100 meter, or no, what did I say? What is the length of a typical jet engine? It's like this, let's say 5 meters, or what, this is 10 meters, so this would be a kilometer. Okay, for laminar flame, and then for turbulent flame, it's small. That is only because of this term. Okay? That term makes all the difference. Okay? This is what we call turbulent mixing. Really, what it does is, you have these eddies, and they move around with their velocity, and they bring stuff from here to there. That's turbulent mixing. Okay. We call this the Reynolds stress tensor. Why do we call it a stress tensor? This is the viscous stress tensor. Why do you call this a stress tensor? Because the mathematical form of that term is exactly the same as this. You see, this is a divergence of a second order tensor. This is the divergence of a second order tensor. Okay? So the mathematical, this is a symmetric tensor, this is a symmetric tensor. The mathematical form of these is exactly the same, which is why, Reynolds, not sure if he called it the Reynolds stress tensor, but this is why we say it must have then the same effect somehow in the fluid as the viscous stress tensor. Okay? So we call this a Reynolds stress tensor, and we know this is the transport. How do you know this is not a production of momentum or consumption of momentum? How do you know this is a transport term? Or we don't know. I call it a transport term. What's the difference between a transport term and a production term? If I integrate this thing over the whole world, then a production term will make the quantity larger. The integral over the whole volume will make it larger. A consumption term will make it smaller. And the transport term will not change anything. It just moves stuff from here to there. Okay? So if I integrate the momentum over this room, the production term will make the momentum smaller in the mean, and the transport term will just move it. How do I know it's a transport term? Because it's a divergence. Okay? Divergence of something, that's always transport term. Because if you integrate over this, integrate over divergence, that gives you just the fluxes over the walls. Okay? So that shows integrating this over space. That shows that this is a term that just moves stuff from here to there. Okay. Okay, now what do we do with this term? And now we're going really, really fast. There's a model for this term because we say it's a transport term. Actually, it's very simple. We say it's a transport term. Well, let's go a step back. So what's the genius of the ingenious part of the Navier-Stokes equations? The Navier-Stokes equations are just a balance of momentum. You don't need to be a genius to maybe a rocket scientist, but not a genius, to derive that equation. It's just a balance equation. Okay. What's the genius is to say tau, to have a model for tau. Okay, and that's where the model comes in the everything else is just balancing momentum, but introducing the viscous stress, relating that to the strain tensor, for example. That is a closure assumption. Okay, that's the ingenious part of the Navier-Stokes equations. And so here, Reynolds just said, no, not Reynolds, but what we do here is just we say, well, if that is mathematically similar to this, why don't we use a similar model also? Okay. So this is the so-called Eddy viscosity model. We say this here should be proportional to the strain tensor, and it should be proportional to a transport coefficient. Now, this is not the molecular transport coefficient as a property of the fluid. This here is not a property of a fluid. But what it gives us, this was a tensor, unknown. It has a symmetric. It has 6 unknown components. This here we know, kind of. This is a part of the solution. These terms, don't worry about these terms for now. So the unknown here is nu t. We don't know nu t. Okay? But we have reduced 9 unknowns to 1 unknown. That's good. Okay, what do we do with nu t? We just do dimension analysis. We say nu t that has the dimensions meter squared over second. That would be a length scale times a velocity scale. And we say an eddy, a turbulent eddy, has a length scale, its size, and it has a velocity scale, which is the velocity with which it turns around itself. And multiplying these two with each other, that gives you a model for this quantity. Okay, just scaling on. Okay, and now the question is, how do you get this u prime? U prime, that would be the velocity fluctuation, and the L, the length scale of this eddy. How do you get that? That's where the turbulence modeling comes in. One model here is the K epsilon model. Very often you say, well, what is the main characteristic of turbulence? That it has these velocity fluctuations. These velocity fluctuations, they can be characterized by the kinetic energy of the velocity fluctuations. Okay? So the kinetic energy of the velocity fluctuations, that would be just, let's say, the contraction of this tensor You see there's a tensor here, we say v prime prime dot v prime prime, that's a scalar. And 1/2 that is the kinetic energy of these fluctuations. We call this K, the turbulent kinetic energy. And that is the main, the most important characteristic of turbulence, kinetic energy. Okay, is this, and then this is my velocity scale already now. The square root of this would be a velocity scale, and now I need a length scale, and I can get this by different ways here without giving any reasons. You can also get a velocity scale by the so-called turbulent kinetic energy dissipation rate, and that then leads to the K epsilon model. Now, epsilon has, epsilon is the dissipation rate of turbulent kinetic energy. By that, it has what units. You can, just from listening to the term, you can guess what the units are. It must be something kinetic energy per unit time. Okay, what is kinetic energy per unit time? That would be meters squared per second cube. Okay, so that's the unit here of this dissipation rate, and just by dimensional arguments, you find that this nu t is k squared over epsilon. Why do we introduce this here? We're not going to solve these equations. We just introduced this model here to say we want to use for scaling arguments later on, when we want to do scaling for turbulence quantities, then we often use k and epsilon to represent velocity scales and length scales. Okay, so then in the k epsilon model, you went backwards actually. I said here we had 9 unknowns, but we reduced it to 1 unknown, and now we went from 1 unknown back to 2 unknowns. Okay, so we need equations for these 2 unknowns. The equation here for k, that can be derived actually relatively easily, and then the models also for the unclosed term, they suggest themselves. What's interesting, if you derive that equation, then you see you have a few transport terms again. Convection term, this would be a turbulent transport of the kinetic energy. This is how the turbulence moves itself around. And then you get a term here like this, which now, if you would integrate this over all space, over the volume of this room, it would not go away. You would find that it's typically positive. And so this here is a production term. And what it shows you here, you see this is the velocity gradient tensor, which shows you when you have shear velocity gradients, then you produce turbulence. Okay, turbulence production is related to velocity gradients. Okay, so that's one thing you see here. The other thing is this here is now minus this epsilon term. Epsilon is a quantity that is kind of a velocity gradient squared. So that's why we call it the dissipation rate. Remember earlier we called it the scalar dissipation rate, or the dissipation rate of mixture fraction. That was also gradient squared. And so here, this is a positive quantity, and because it has a minus here, this must be removal of turbulent kinetic energy. Okay, so this is the dissipation, which happens at small scale. So this here is actually velocity gradient squared times the kinematic viscosity. Okay, so it's very similar in form to the scalar dissipation rate that we introduced earlier. There's also transport coefficient times gradient squared. Okay, so this is this. There's the epsilon equation. Then, so we solve or we can solve an epsilon equation also. This equation is a little more empirical, and especially the closure here for production and dissipation terms are a little more empirical. But this can be closed then, and there are a lot of coefficients that appear here, especially in the epsilon equation, which are often set to these values. Now, as I mentioned earlier, if you want to use this for a, let's say a planar jet, this would work fine. If you want to use it for a round jet, then you would see that these coefficients here are not very good, and people have different coefficients that you would use for a round jet. Okay, okay, so this is a part here that I want to skip. This now comes to the, you know, the Kolmogorov theory. Kolmogorov theory tells you, let's say, two things. It tells you that there's an energy cascade, like we discussed earlier, and the two-point correlation. So the energy cascade. Let me show you this first, and then I'll show you what we're skipping, in case you want to look at this. The energy cascade is often described in a plot like this. What is this? This is a Fourier transform of the two-point correlation, whatever this is. But what it gives you, what it tells you, and it's a function of the wave number of the turbulence. What's the wave number? The wave number is basically 1 over the length scale. Okay, so high wave number means very small eddies. Small wave number means large eddies. Okay, and so this tells you how much energy you have, kinetic energy you have per wave number. Okay, so what this means then here, and this is a logarithmic plot, it's a log plot, and what it shows you here is that there are certain length scales where the energy is very large. The turbulent kinetic energy is very large. And if you go to smaller length scales, which means larger wave number, the turbulent kinetic energy gets smaller and smaller. Okay? Now, this is a logarithmic plot, which means so this is a lot of energy, and if I go here, then there's no more energy. So the energy here in these eddies essentially can be neglected for the total energy, okay? The total kinetic energy, which means that all the energy is actually contained, the kinetic energy is contained in the large scales. That's why the large turbulent scales, they're responsible for mixing, okay? The small turbulent scales, they do some other stuff, but they don't really contribute a lot to the, let's say, the overall mixing effect. The small scales do then the molecular mixing, but not bringing stuff from here to there. That's what the large scales do. Okay? And then when you go to very, very small scales, this very high wave number, there's not much energy in these small scales, but the gradients now become very large, as I mentioned, and viscosity dissipation becomes important. So this here is where you see that now here the kinetic energy, it totally goes away, and this because of dissipation. And so at the small scales, the dissipation happens. And now, if production of energy is all here, and dissipation of energy is all there, there must be a mechanism that converts the energy of the large scales into smaller scales until it can dissipate. Okay? And that is the so-called vortex stretching. But then what the Kolmogorov theory here says is there is a length scale regime of eddies that where you look at a range of scales that is much smaller than the large scales of the turbulence, but much larger than the small scales of the turbulence. In that regime, the production of turbulence is not important, and also the dissipation of turbulence is not important. All that's important is just a transfer of energy from large to small scales. Okay? And by making that assumption, you can find out that then the turbulence statistics here should be dependent only on one single parameter. That single parameter is often used, the epsilon is used at that parameter, and scaling arguments that tell you that the slope of this should be of E, should be, or actually the function here should be a universal constant times epsilon to the 2/3 times k, the wave number, to the minus 5/3. So that's Kolmogorov's famous minus 5/3 law. And you know, probably most here have heard that term before. Okay? So that's called the inertial subrange, because here only the inertial, you know, forces are important. Viscosity is not important. Okay. Okay. So so that's the one thing that that the Kolmogorov theory tells us, And now if you want to, so that was all done in spectral space. Okay, we talk about wave numbers. But then also you can do the same thing in physical space. And that then starts with a so-called two-point correlation. You know, we just defined here. And again, you can look at this if you want. And you get something similar to the minus 5/3 law. And it is an R to the 2/3 law. Okay? So that's the same thing. And but we'll skip over this. Now, one thing that's important is to define turbulent time scales, velocity scales, and length scales, and that is done here. So now we want to define the length scale of the large eddies of the turbulence. We want to define that by using the spectrum. The spectrum, and essentially say where the energy, most of the energy is. That's what we want to say. That's where the the large scales of the turbulence are. And one can find this by looking. Now I do have to talk about the two. I thought I could skip this two-point correlation, but I need it now anyways. So let me tell you what the two-point correlation is, because in order to introduce the large scales of the turbulence, we need this. Okay, so two-point correlation is this. I measure at the same time the velocity fluctuation at this point and at this point. Okay, and then I look at how they correlate. And now you can imagine if I move these 2 points very, very close together, then they correlate perfectly. Okay? If they're the same place, they correlate perfectly. If I move them very, very far away from each other, they don't correlate at all. Okay? Now, imagine you have a turbulent eddy that goes like this. Okay? That's the largest turbulent eddy I have. I don't have any larger eddy. Okay? Then, if I move the 2 points within this eddy, they're still correlated. Okay? If I move outside of this eddy, they're not correlated. Okay? So, this 2-point correlation is shown here. So you see the distance between these 2 points. That would be a coordinate or an independent coordinate here. And I can normalize this with the kinetic energy. If I make r equal to 0, both points at the same point, that gives me the kinetic energy. Okay? So I divide this by the kinetic energy at r equal to 0, it would be 1. Very, very large separation distance, it goes to 0, no correlation. But then you can say, well, where I still have appreciable correlation, you know, I must be within my large eddy. And so what you do here is you just, in order to define a length scale, you just integrate over the whole area here and divide it by 1, and that basically tells you that would be a square, or that would be a rectangle here that has the same area as what's under this curve. And you say that's the so-called integral length. That's a measure for the correlation, for the largest correlation distance. And because it's defined with this integral, we call it the integral length. Okay, so now I can go back to my length scales here, and that's shown here. So f is this 2-point correlation, the normalized 2-point correlation, and the integral over this f function that has units of a length scale, and so that should be the large correlation length scale, and we call this the integral length scale. And again, it turns out that is the length scale where the turbulence has most of its kinetic energy. So that's a very important one. Velocity scale can be, fluctuation scale can be defined from the turbulent kinetic energy. That's just a square root, basically, of the turbulent kinetic energy. So that's kind of a turnover velocity, and then you can define, with these two then, you have a length scale and a velocity scale, you can define the time scale also just by L divided by V prime. So one thing I mentioned earlier is that for most of this energy spectrum I was showing you earlier, or this inertial subrange, we said that inertial subrange, it's just scales with one parameter. There's only one parameter that controls this, and that is the epsilon. And epsilon, we call it the dissipation rate, but also it's the energy transfer rate in this inertial subrange. So this energy transfer rate is very important, and so it can also be used here to define a time scale of the large scales of the turbulence by, k divided by epsilon. Now, these are the large scales of the turbulence. We said earlier there are also small scales of the turbulence, and we want to see what is the smallest scale of the turbulence, because that will be important later on for the interaction of a turbulent field with a reactive flow, with a flame, for example. It matters if a flame is thicker or thinner than the smallest scales of the turbulence. Okay? So the smallest scales of the turbulence, then they depend on the viscosity. That's what we said earlier. And using this parameter epsilon and u, you can define a length scale, and that length scale is nu cubed divided by epsilon to the 1/4, and that is the famous Kolmogorov length scale. That's the smallest scale that you find in a turbulent flow. The smallest length scale you find in a turbulent flow. With epsilon and u, you can also define a time scale like this and a velocity scale like this. And so these are the smallest scales. The smallest scales in the turbulent flow, and then the integral scales are the largest scales in the turbulent flow. Now, one thing that's interesting is, and then earlier I said there are two things really we learned from the Kolmogorov theory, or maybe three. I mean, the smallest scales of turbulence, that's one. The second was that there is this inertial subrange, where everything, the kinetic energy, let's say, depends only on epsilon and the wave number that you're looking at. And the third, that is very important, is the so-called Kolmogorov scaling. And that actually is the same. It's just a consequence of what I said about number 2. The Kolmogorov scaling essentially tells you that, again, in the inertial subrange, the turbulence statistics, so the kinetic energy, depends only on the wave number and the kinetic and the dissipation rate. Which means that in the dissipation rate, that energy transfer rate, that's the same at all wave numbers. Okay? So that means we can also write the integral length scale as essentially using the integral velocity scale and epsilon. Okay? And it just comes out, dimensionally it just comes out this way. Epsilon is then v prime cubed over L. But because this must be true, because all scales, all length scales, they just scale with epsilon, this relation must be true also at other length scales. So when I say epsilon must be v prime cubed over L, then it also must be v eta cubed over eta. So you can form epsilon with the smaller scales, with the larger scales, and with all other scales also. And that provides you a way to relate different scales to each other. Okay? That's the Kolmogorov scale. So from this follows then that I could also say v eta cubed over eta is equal to v prime cubed over L. Okay? And that, for example, you just write that down. That gives you a relation between the smallest and the largest scale. Okay? And that gives you, you just write this down. That gives you the relation eta over L is equal to Reynolds to the turbulent Reynolds number to the minus 3/4. Some of you might have heard this or might have seen this. But that just follows from what I just said. Okay? Equating this with this. But it also is true for all other scales, not just for the smallest and the largest. It's true for all scales. So that's what we call the Kolmogorov scaling. Okay, so we talked about this. the what? We talked about this energy spectrum and the consequences. Okay, so now what we want to do is, now we want to talk about combustion again. Talk about the equations for the scalars, and then also maybe some attempts to provide closure for these equations, and then talk about some other models. Before then, we go back to talk about maybe some more empirical models also, and other models. But then we want to go back and talk more about the physics again of premixed combustion, and then of premixed turbulent combustion, and then turbulent non-premixed combustion. Okay? Any questions about this very short crash course on turbulence? I bet there must be 1,000 questions left, and we can probably not answer all of them. Okay, I'm glad. Let's move on quickly. So, these are the balance equations for the reactive scalars. Just like earlier, we derived equations for the mean momentum or mean velocities. We can also derive equations for the mean, the averages of the scalars. And then again here we get a there's a nonlinear term here. We get a transport term from this. You see that. That's the so-called scalar flux term. It's just the turbulent transport term for the scalar. We'll see that on the next page. And then you see here, we have the source term. If you average the source term is a very nonlinear term. So you get very nonlinear stuff coming out of this. And that's the problem, really, in turbulent combustion. Now, you see this, the temperature equation is the species equation. They look very similar, especially if we assume that the Lewis number is equal to 1. They look almost identical. This has a chemical source term, this has a chemical source term. The source terms are different, of course, but we typically just say we have scalar equations, could be mass fraction, could be temperature. We write it like this, and sigma here, that's a source term, okay? And you just have to know how that source term looks like, but essentially they're the same. Okay, so if you introduce these averages, you get this. You see this here is the scalar flux term I just mentioned. For this, again, we can make this radiant transport assumption. So that will look very similar to the actual molecular transport term, except it has a turbulent transport coefficient, and we can model that again, similarly to what I told you earlier. So that's the turbulent transport term. This is the laminar transport term, or the molecular transport term. Turns out, in turbulent flows, or in this Reynolds average approximation, I said this earlier, the smallest possible, for the smallest possible Reynolds number where you get a turbulent flow, the turbulent transport is at least 100 times faster than the molecular transport, okay? So in these equations here, we know this term here will always be at least 100 times smaller than this. And so typically, this term here is neglected. Okay? And so this is easy, this is easy, this is neglected. This is, yeah, we can close this, let's say, and then we are left with this term. That's the problem. How do we close this term? This term is now the average of, we said temperature squared, or fuel times oxidizer times exponential minus E over RT. Introduce your decomposition there, and you get something very, very complicated correlations, which we, need to model, or we don't know a priori how to model this. Do you have a question? Because the gradients here, see this term here is also built essentially now. Let's say for just for the sake of argument. Rho and D are constants, okay? Then this here also is the mean, okay? And this is a good question, actually. So you have two terms. One looks like this. What do we have? C. And the other one looks like this. Once I introduce the model, it will look like this. C, and this is the mean, and this is the mean. Okay? So, there's no difference except for this is a turbulent transport coefficient, this is a molecular transport coefficient.
The mean is on the whole term. I think that's the difference.
Yeah, but no, but I said here, let's say these are constant, so they're not fluctuating quantities. So I just, I just put it here. Or put the bar. I mean, that's fine. Doesn't matter. What I want to say, the only difference between these two is that transport coefficient. And the transport coefficient now, the ratio between these is this. Okay? Now, go back to the viscosity. It makes it a little easier to think about it. That would be something that looks like this. Turbulent eddy diffusivity, eddy viscosity, and viscosity. Now, I said earlier, how do we model this new T? I said we model this as U prime times L, the integral length scale. Okay? So if I do this, what do I have? Is a Reynolds number. This is the turbulent Reynolds number. So here I assume, from here to here, I just assume the Schmidt numbers are 1. Okay? So this here then is turbulent Reynolds number. Turns out in a turbulent flow, this is at least 100, let's say. Okay? Which shows you that as soon as the flow is turbulent, this term is at least 100 times larger.
The gradients, the actual value of the gradients would be like when you solve it would be equal. However, like in a physical way, these gradients aren't taken in the small scales because it's very small.
Yes.
The other in the
That's
large,
right.
like large.
Exactly. But so what you're saying is the local instantaneous gradients in a turbulent flow, they're much larger. But they don't appear here. Okay? This term here, that is the term that relates to the mean gradient. Okay? Only when you get correlations of because it's a linear term, the fluctuations fall out. If you have a nonlinear term, then these matter. Okay? And that's here, for example. This is why this here, for this term, the small scale fluctuations matter. Okay, so let's see. I want to show you what happens if you model this term in a very naive way. Okay? So now let's look at isotropic turbulence. Isotropic turbulence. That's the simplest form of turbulence. Just take a box and it has turbulence in it, let's say. And then in that box, I want to say I have blobs of fuel and air. Okay? And now I let the turbulence mix this, and I let it react. In the beginning, the temperature averaged over the box is relatively low because I have a lot of cold fuel and air. And while I let it go, let it react with each other, the mean temperature averaged over the whole box, it increases and goes up. Okay? These are the physics. Because isotropic turbulence, as I said, just take a box that's full of turbulence. It doesn't have a directional dependence and so on. It's homogeneous. These terms here, they drop out. Okay, that's a nice thing about isotropic turbulence. So only the first term and the last term remain. Okay, that's this. Okay, now what I can do is so this here actually is the result of a direct numerical simulation. So that's what we think is the truth. Solving the full transport equation. Now, as I said, if I let this go in the beginning, the temperature is relatively low, and while fuel and air mix and react, the overall temperature in the box becomes larger and larger. Now, what if I say this here is a chemical source term? So it is basically fuel times oxygen times exponential minus E over RT. Now the average of this, introducing this Reynolds decomposition, that gives me a lot of these very complicated correlation terms. What if I neglect all these correlation terms and say I evaluate the source term just with the mean oxygen mass fraction times the mean fuel mass fraction times exponential minus E over RT mean. Okay? That would be the simplest thing to do. Then you get this. Okay? Nothing happens in this box. If you use the, flamelet closure assumption, we'll talk about this later on. We derived these flamelet equations already, and you see it's not bad, actually. But the point is, neglecting closure leads to a leading order error. This is not a small error you make. That's a big error you make. And now, in most of the commercial codes you use, they will tell you, when you want to do a turbulent combustion problem, they say, oh, just solve detailed chemistry, and they don't do any closure of the chemical source terms. Okay, they just evaluate the source terms just with a mean. That's computed from solving that equation. Okay, so just solving moment equations and closing this with a mean, that is wrong. Okay, that's all I want to say. Okay, so we mentioned earlier that the scalar dissipation and also scalar transport, they're important in turbulent flows. And so the question is, how do we model these? And so important here is, so we can introduce models for the scalar flux, first of all. Here we use just the example of the mixture fraction as a non-reactive scalar. We see for non-premixed combustion, this would also hold for other scalars. For premixed combustion, this assumption that we make here is actually not all that good. But again, I'm coming back to making the exact same assumption. This is the molecular flux. Fixed law. Fixed law. That's just a closure model that somebody introduced into this species transport equation. So because this here we know it's a scalar flux, just like the molecular flux is a turbulent flux, has the same form in the equation. We want to make this look similar to the molecular flux, and so introducing this assumption is proportional to the gradient times a transport coefficient. So this is like fixed law, just with a turbulent transport coefficient, and that gives you then the same term as I showed earlier. And then we can have a model for this. And here after we just say we assume the Schmidt number, turbulent Schmidt number, is nu t over dt, and we just assume that's equal to 1 or 0.7 is what people often use, and that relates then to diffusivity back to the viscosity. And for the eddy viscosity, we had a model earlier that was based on the K epsilon model. Okay? That's how we model the scalar flux in these equations. And so this, we can derive an equation here for the mean for the mixture fraction that's given here. Now, and this is now where you really see that this concept of the mixture fraction, using the mixture fraction, pays off, because I said this equation here, that can't be solved really, because we don't know how to close this term. However, this equation, it can be solved because it doesn't have to be solved. Okay? So this is an equation that we, can solve with the model, set of model term. We can solve this with good confidence. Okay? Now, turns out, just like to describe turbulence, we need the mean and the turbulent fluctuation. The turbulent fluctuation was characterized, of the velocity was characterized with what quantity? With a turbulent kinetic energy. Just like we need the information about the mean and the fluctuation, also for the scalar we need information about the mean and the fluctuation. And later on, when we talk about non-premixed combustion, you will see why we need that information. But we can also derive an equation for the so-called scalar variance. Okay, so this is the mean equation. No, this is the mean equation. I'm sorry, this is the mean equation. This is the instantaneous equation. You subtract the mean from the instantaneous, you get an equation for the fluctuation. Well, this is how it looks like. You multiply this by z prime prime, and then you see you get an equation here for 1/2 z prime prime squared. Okay? And you average this, and this gives you an equation here for the variance of mixture fraction, or the fluctuation squared of mixture fraction. And you see an old friend in that equation. Production term, that's also a good old friend, but the dissipation rate, okay? Here we see the dissipation rate appearing again. And now, you know, it kind of makes sense that what we talked about earlier, what does the dissipation rate do? You have, let's say, a mixture fraction profile that looks like this. Now, in the turbulent flow, it kind of looks more like this. Okay? And anytime what this thing does is it essentially takes out these fluctuations. And anytime you take out these fluctuations, you actually caused molecular mixing to happen. And so this is why this dissipation rate in the laminar formulation and also in the turbulent formulation appears here. So we need to model this dissipation rate. So this is the definition here. And you see the definition is, so this average, it's over the squared, right? So this is the gradient of the velocity of the z fluctuation squared, and then the average, and then times the difference. Okay. Okay, so we have now a model for the, we have a transport equation for the mean. We have closed this. We have a transport equation for the variance. That is actually closed except for the dissipation rate. So all we need now is a model for the dissipation rate. And the model for the dissipation rate is, it comes from a time scale argument. The argument is that we said earlier, a time scale, the integral time scale of the turbulence is the integral time scale of the turbulence can be written like this, is k divided by epsilon. Okay, the kinetic energy divided by its dissipation rate. Okay? And similarly, the time scale for the scalar can be written as the variance over the dissipation rate. You see that this is exactly the same, because the variance, this variance for the scalar is the same as the kinetic energy, you know, for the velocity field. And so the assumption here is that both of these timescales are the same. This timescale and this timescale, the scalar timescale and the so-called mechanical timescale are the same. You know, if I set these equal or proportional, then you get an expression like this. Chi is equal to epsilon over k times the variance. Okay? And there's a coefficient here. That coefficient, you see, that's not a constant, but you know, the model we assume it's constant. The value of 2 here is often used, but if you see, if you introduce this here back into this equation, the equation is closed. Okay. Now I just need epsilon and k, but if I solve the k epsilon model, then the equation is closed. Okay. Good. See where we are. So we have to go 5 minutes longer. Otherwise, you will have to stand too long in the line. The food. What is that? Oh, the photos. So there's no. Oh, so that's 12:15, right? Yeah. So does that mean we have to stop now? That's too bad. I wanted to trick you again into this line thing, but I thought when they suggested this yesterday, I thought, oh yeah, that makes sense. They rather sit here and work hard than standing in the line and talk to each other. Yeah, good students. Okay, so let's stop here then, and we'll continue this tomorrow. So there won't be any time now for questions. I enjoyed it actually. I don't know. Well, maybe you know, while we walk to the photo, you guys can ask questions.